In the first lecture on canonical transformation, you have seen the definition of canonical transformation. Actually, you have seen that a transformation of phase space is actually known as canonical transformation. It means there will be a transformation of position and momentum coordinates, but in such a way that the canonical equations of Hamilton do not change its form. That is, the form of Hamilton's equation remain invariant, or they preserve their forms. Then you say that the transformation is canonical. And so for your convenience, I have actually mentioned here all the things which we have discussed in the first lecture on this canonical transformation. Today our aim is actually to find the generating function for this transformation. And for that I have mentioned here the resume of the previous lecture. You can see here that a small qk and a small pk, these are actually the position and momentum coordinates in the old coordinate system. And when you change the coordinate system to a new coordinate system, then you have assumed that the position coordinate is denoted by this capital QK and momentum coordinate by capital PK. And as you know, the Hamiltonian and Lagrangian in old coordinate system we denote by the symbol H and L, while in the new coordinate system we denote them by the symbols H prime and L prime. And you have seen that a transformation like this, qk equal to qk of a small qk, small pk and t, and capital pk equal to capital pk, that is new momentum coordinate, of a small qk, a small pk and t. These transformations are known as canonical transformations, but only when the variables qk and pk, that is capital qk and capital pk, are also canonical variables. Only then you can say that these transformations are canonical. When you say that these capital qk and capital pk, that is the new position and momentum coordinates, are canonical variables, what does it mean? It means that in terms of these coordinates, the form of the Hamilton's canonical equations of motion do not change. It means if you define the Hamilton's canonical equations of motion in this new coordinate system, then they must be in this form. That is, qk dot is equal to del h prime by del pk, and pk dot is equal to minus del h prime by del qk. Because you know these are the forms of the Hamilton's canonical equation. So you can say that if these Hamilton's equations of motion get satisfied, only then the transformation defined by these equations, let us say in equation A, are known as canonical transformation. Again, you know the definition of Hamiltonian. In old coordinate system, you define the Hamiltonian like this: H equal to summation over K pk qk dot minus L. Similarly, in the new coordinate system, the Hamiltonian H prime will be equal to summation over K capital PK capital QK dot minus L prime. Here, in fact, this K runs from 1 to n, that is K equal to 1, 2, 3, 4 and so on, and n. So these are the facts which we have already discussed in the previous lecture. And as I have told you that in present lecture our aim is to find the generating function for these transformations. That is, a function which will furnish such a canonical transformation. Our aim is to find that very function in this lecture. So let us start to find a function which will furnish the canonical transformation. So you can say our aim is to discuss the generating function for canonical transformation, or the condition to obtain that a transformation is canonical. And as you know, the Hamilton's variational principle, or modified Hamilton's variational principle, is an outcome of the Hamilton's fundamental equations of motion. So if this new coordinates, that is capital QK and capital PK, are also canonical, then they definitely satisfy the modified Hamilton's principle. And you know the form of modified Hamilton's principle because you have already studied this modified Hamilton's principle in the previous lectures. So if QK and PK, that is capital QK and capital PK, that is the new position coordinate and the new momentum coordinate, are canonical variables or canonical coordinates, then they must satisfy this modified Hamilton's principle, which is written as delta integral T1 to T2 summation over K, where K runs from 1 to n, PK QK dot minus H prime. And as you know, H prime is a function of QK, PK and T, dt equal to 0. But you know that the old coordinates, that is a small qk and a small pk, are already canonical because they satisfy the Hamilton's canonical equations of motion. So they are already canonical, and so definitely they satisfy the Hamilton's variational principle. So for these coordinates, you can write the Hamilton's modified variational principle in this way, that is delta integral T1 to T2 summation over K PK QK dot minus H of QK PK T dt equal to 0. Now as you can see, equation 1 and 2, the RHS in both equations are equal to 0. But this equality does not refer that the integrands of both equations are same. In fact, the simultaneous validity of these equations 1 and 2, as their right hand side is 0, does not mean that the integrands of the two integrals are equal. So you can write these two equations in a combined form. So the simultaneous validity of equations 1 and 2 does not mean that the integrands of or in the two integrals are equal. So we can write in a combined form equation 1 and 2 like this. Therefore, you can write delta integral T1 to T2 summation over K PK QK dot minus H and minus summation over K capital PK capital QK dot minus H prime dt equal to 0. And let us say this is equation 3. In fact, in this equation 3, the integrand is not known to certain extent. In other words, you can say that the integrand of this equation 3 is something uncertain. We do not know what is this integrand. Now you can see that this equation 3 will remain unaffected if we add or subtract from it the total time derivative of an arbitrary function f, which will be actually a function of q, p and t. You can see it. I will check it how you can say that when we will add or subtract from this integrand a total time derivative of an arbitrary function f, which will be a function of q, p and t, the result will remain unaffected. So we can see that equation 3 will not be affected, if we add to or subtract from it a total time derivative of an arbitrary function f equal to f of qk pk t. You can check it, as you can check it that when you will add actually the df by dt in the integrand of this equation 3, you will see the result will remain unaffected. So you can see how this is possible. As let us try to evaluate this term delta t1 to t2 df by dt, because when you will add df by dt in the integrand, then this integral and this delta operator will be operated on that. So I am evaluating delta integral t1 to t2 df by dt. Now you can see that this f is actually a function of variables qk, pk and t. So this may be written as delta f of qk, pk, t, because you know this integral of df by dt will be simply equal to f, and limits here are actually t1 and t2. Now take the operation of this delta operator on this function f. Since f is not a function of only one variable, but this is a function of qk, pk and t, so we must follow the rules of partial differentiation. So you can see this will be what? This will be del f by del qk, here there will be summation, in fact, del f by del qk delta qk plus summation over k del f by del pk delta pk and plus del f by del t delta t, and limits are t1 and t2. But as you know, this delta t is actually equal to 0, because in delta variation for all the paths times are same. If you move from this point A to this point B along these two paths, times for both paths remain same. So this delta is equal to 0 in delta variation. So the last term will vanish, and you can see this will be summation over k del f by del qk delta qk, and limits are t1 and t2, plus the next term will be what? This will be summation over k del f by del pk delta pk, and the limits are t1 and t2. But as you know, you have studied in the calculus of variation that at the end points, that is at time t1 and time t2, this delta qk and delta pk also vanish in this delta variation. So at the end points means at time t1 and time t2, at end points this delta qk is equal to delta pk and both are equal to 0. So you can say that this whole result is equal to 0. So you can write, therefore, delta integral t1 to t2 df by dt dt, this is equal to 0. So now you can see, since this integral is 0, that's why I have told you earlier that when we will add actually the df by dt in this integrand of the equation 3, the result will remain unaffected. So you can write this df by dt here either in plus form or in minus form, because we can add this df by dt in this term, or we can subtract df by dt in this term, and the result will remain unaffected. And that's why you can write now this equation 3 in this way. So equation, what is the equation number? Equation number 3. You can see, so the equation 3 can be written as, delta integral from t1 to t2 summation over k pk qk dot minus h, this is inside the first bracket, minus there is summation over k capital pk capital qk dot minus h prime, this is the new Hamiltonian, and minus df by dt. You can also write here plus df by dt, because we can add or we can subtract this df by dt in the integrand, but result will remain unaffected, and this will be equal to 0. In fact, as it is a definite integral, and so for all values of this result will be valid only when the integrand itself is equal to 0. So you can say that it follows that summation over k pk qk dot minus h and minus summation over k capital pk capital qk dot minus h prime and minus df by dt, this equal to 0. Or equivalently, you can write this expression in this way. This is summation over k pk qk dot minus h minus summation over k, where k runs from 1 to n, remember, pk qk dot minus h prime, and this is equal to df by dt. This is equal to df by dt. You can see. And what will be the equation number? This is, say, equation 4. Now, after getting this result, we can see the idea or the concept of generating function. Let us observe this equation 4 seriously. You can see in the first bracket of this equation 4, see this first bracket. In this first bracket of this equation, you can see the variables are in fact qk, pk and t. And similarly, the second bracket, you can see here that the second bracket is as a function of capital qk, capital pk and t. So in general, this function f, which is just an arbitrary function, you can say that this function f is in general a function of 4n plus 1 variables. How this is 4n plus 1? Because you know k runs from 1 to n. So a small pk will have n values. Similarly, a small qk will have also n values. So there will be 2n values of a small pk and a small qk. And similarly, the capital pk has also in fact n values, that is p1, p2, p3 to pn, and capital qk will have also n values. So there are total 2n values of capital qk and capital pk. So there will be 4n values of a small qk, a small pk, capital qk and capital pk. And one of the variable is time t. So as a whole, you can say that this function f will be actually a function of 4n plus 1 variables. You can see. Thus, f is a function of 4n plus 1 variables. 4n plus 1 variables. And what are those variables? You can see these variables are qk, pk, again capital Qk, capital Pk and T. In fact, this small qk and small pk, the total number will be 2n. Again, for capital Qk, capital Pk, total number will be 2n, and for this t, the number will be 1. So as a whole, you can say that this function f is a function of 4n plus 1 variables. But now let us see the transformation equation. You know the transformation equation, that is the canonical transformation. You know this is qk equal to qk of a small qk, a small pk and t. And similarly, capital Pk equal to capital Pk of a small qk, a small pk and t. You know, these are the transformation equation. So, observing these transformation equation, you can see that out of this 4n variables, only 2n variables will be independent. Only 2n variables will be independent, and the time variable will remain same. So we can say that the two sets of the transformation equations defined here, we have out of 4n variables, there will be only 2n independent variables. So you can say that among these 4n variables, only 2n are independent variables. So among 4n variables, there are 2n independent variables. 2n independent variables. Now, f is an arbitrary function you have considered, and this f is actually a function of both old and new set of coordinates, and therefore we must select n variable from the old set and n independent variable from the new set to express this function f. So you can say as f must be a function of both old and new variables. So definitely we have to consider the n independent variables from the old set and n independent variables from the new set, as f must be a function of both old and new variables. So we must select n independent variables from the old set of coordinates, and n variables from the new set of coordinates, set of coordinates. So in this way, you can see there will be actually the 4 forms of this function f. So what are those 4 forms? Selecting n variables from old set and n variables from new sets. So you can say that 4 forms of f will be there. And what will be those 4 forms? You can see. If you denote the 4 forms of this function f by the symbol f1, f2, f3 and f4, then you can say that the first form f1, you can choose this f1 as a function of qk, small qk, capital qk and t. You can see this small qk will have actually the n values. Similarly, the capital qk will have also n values and t has 1 value. So as a whole, these are actually 2n plus 1 independent variables. And at the same time, you can see that this small qk are the coordinates from the old set of coordinates and this capital qk from the new set of coordinates. Similarly, you can choose the another form f2, and this f2 is may be taken like this. This is qk pk t. Again you can see qk has actually n values, this capital pk has n values and t has 1 value. So in fact these are as a whole, these are 2n plus 1 independent variables. And again a small qk is from old set and capital pk is from new set. Similarly, you can choose the third form of this function f3, and we can choose it like pk, qk and t. And the fourth form you can take like this, f4 of pk, capital pk and t. Actually these are the 4 forms of this arbitrary function f. In fact, this function f, which has actually these 4 forms, are known as the generating function for the canonical transformation. So f is known as generating function. And this generating function has actually 4 forms, and how we will select the independent variables in expressing the different form. You can see you have to consider one variable from the old set and another variable from the new set, and this time coordinate will remain at is in every form. Now without doing the calculation, or you can say without doing the rigorous calculation of the derivation for the transformation equation in terms of these generating functions, I am here just going to write all the forms, and I will also interpret a technique how to remember this transformation equation. But in the forthcoming lecture, we will start to derive those relations, but here I am just mentioning those relations directly. So you can see what is the first form of transformation equations. So the transformation equations. And first form. When you consider the first form, you know the first form of generating function is f1 equal to f1 of qk, capital QK t. Remember, if you know If you have expressed this generating function as a function of a small qk, capital Qk and t, then you have to find a small pk. If here is qk, the conjugate momentum will be a small pk, and if here is capital qk, then the conjugate momentum will be in fact capital pk. So we have to find a small pk and a small qk in this case. Remember it. So, and how that will be found, you can see. If you want to find this small, this is just a technique, this is not actual derivation. So, because I have told you how I will discuss a technique how to remember these transformation equation, and this is actually very important for competitive examinations, because in competitive examinations the rigorous derivation is not asked, but you have to remember these forms. So you can see, if the function is a function of qk, we have to find a small pk, and as for getting the value of a small pk, you have to differentiate partially this f1 with respect to qk. So pk will be equal to del f1 by del qk, and the another transformation equation will be pk. Since it is a function of capital qk, so its conjugate momentum will be capital pk, and so, and this will be equal to minus del f1 by del qk. And you know, the new Hamiltonian differs from the old Hamiltonian by the time derivative of the generating function. So h prime will be equal to h plus del f1 by del t. One thing remember here, for the sign you must remember that if you write here qk, pk, again capital qk and capital pk, remember one thing, if you differentiate with respect to qk, then you should take plus sign. When you will differentiate with respect to this small pk, then you have to take minus sign. This is just a technique. And when we will differentiate with respect to capital qk, then again we have to take minus sign. But when we will differentiate with respect to pk, we will take plus sign. Remember this technique, and remembering this technique, you can write the sign of the derivative. Now see the transformation equation of the second form. You know, the second form of generating function f2 is what? f2 is equal to f2 of qk, pk, t. Now I will ask you how we can write the transformation equation. Since here is in the argument qk, so we have to find pk. And for finding pk, what you will do? I have just mentioned the technique. You have to take the partial derivative of this f2 with respect to qk. And now see the sign. I have mentioned here that if when we will differentiate with respect to qk, we will take plus sign. So here will be plus. Now since in the argument is capital pk, so we will have to find capital qk. And what will be this? This will be the partial derivative of f2 with respect to this pk, del pk. And see the sign. You can see when differentiation will be with respect to capital pk, we have to take plus sign. So here both term will be plus. And again, the new Hamiltonian in this case 2 will be equal to h plus del f2 by del t. Now you can see the third form of the transformation equation. What is the third form? You can see F3 is equal to F3 of Pk, capital Qk and T. Now you can write the transformation equation on the basis of the facts which I have just discussed. See here, in the argument there is Pk, so we must find a small qk. And for that you have to write del F3 by del Pk. Now see what will be the sign. Since we are differentiating with respect to Pk, so you should take minus sign here. So this will be minus del F3 by del Pk. Again, here is capital Qk, so we will find capital Pk. And for that we will differentiate F3 with respect to this capital Qk. And now see the sign. When differentiation will be with respect to capital Qk, I have told you a technique that you have to take minus sign. So here will be minus again. And again the new Hamiltonian in this case too will be old Hamiltonian plus del F3 by del T. Now see the fourth term. Fourth form. What is the fourth form of generating function? You can see this is F4 of a small pk, capital Pk and T. Now see, in the argument there is a small pk, so you have to find a small qk. And for that, now I hope you can do it. This will be del F4 by del Pk. And what will be the sign? See here. Since differentiation is partially with respect to Pk, so you have to take minus sign. So here will be minus, and now there is capital Pk in argument, so you have to find capital Qk. And this will be what? This will be del F4 by del Pk. And you can see when differentiation is with respect to Pk, we have to take plus sign. So this will be plus. And again, the new Hamiltonian H prime will be equal to the old Hamiltonian plus del F4 by del T. So these are the transformation equations in the four forms of the generating function. But as I have told you that in this lecture I have mentioned the technique, the trick, and this trick is actually very useful to remember these transformation equations and solving the numerical problems, particularly in competitive examinations. But in university examination, questions will be also asked to derive these results. So in the next lecture, we will see how these transformation equations can be obtained by the rigorous method.